Hello geometry students, my name is Emigh, and this video is our discussion on section 2.2, Patterns and Inductive Reasoning. Inductive reasoning, it is the process of arriving at a conclusion. Sometimes that conclusion is called a conjecture or an educated guess, based on observing patterns and observing specific examples. So we're going to use inductive reasoning here to make a conjecture or an educated guess, a conclusion basically. All right, look for a pattern in each list. Predict the next two terms. Okay, so list A is our first list, and our first term is -2, followed by 10, followed by -50, followed by the term 250, and so we are supposed to predict using inductive reasoning what the next two terms are going to be. Part B, same thing. We've got 1, 1, 2, 3, 5, 8, 13, 21. Based on that pattern, we're supposed to predict what the next two terms are going to be. And same thing for part C. Make a conjecture about the color and number of regions in the 30th circle. So if this is 1, 2, 3, 4, our fifth one would be pink with 1, 2, 3, 4, 5, 6, 7, 8, 10 segments. So what about the 30th one? Would it be pink or blue, and how many segments would it have? All right, I'd like you to pause this video now and try A, B, and C. Okay, welcome back. Let's see how you did. Check your own work. If you came up with part A having the next term to be negative 1,250, you're right, followed by the next term positive 6,250. And you got part A right. And the pattern was multiplying the previous term by -5. So if you notice that the signs were switching. Whenever your signs go negative, positive, negative, positive, that means you're multiplying by a negative number or dividing by a negative number. And to get from 2 to 10, you could have added 8 or multiplied by 5. So if you continue with that thought process, adding 8 would only get us to 18. So, oh gosh, I should have said adding 12 to get all the way from -2 to +10. So adding 12 would not get us to -50, but multiplying by -5 would. So part B, the next two terms are 34 and 55. And the pattern, what was happening there is that you're adding the two previous terms together. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and 5 plus 8 is 13, 8 plus 13 is 21, and 13 plus 21 is how we get that 34. And then 34 plus 21 is how we get the 55. Okay, part C. If you said that the 30th circle, just a note there, sorry. The numbers in part B, those are actually the first 9 terms of a list of numbers called the Fibonacci sequence. Happens in nature a lot. If you want to look it up, you can see a lot of cool visuals in a story on Fibonacci. Okay, part C, if you said that it would be a blue circle and that it would have 60 segments, then you got it right. I will say though that there are some other options that you could have come up with that could also be right. You may have decided that the pattern is going to go 1, 2, 3, 4, and then maybe it's going to backtrack. Maybe it's going to do the fourth one again, and then the 6th, the 7th, the 8th, and then backtrack again, 9, 10, 11, 12. There's nothing that really shows us that is incorrect necessarily. So that's why sometimes it's an educated guess. If you got the blue 60, we're assuming that the pattern continues in this direction. Pink, blue, pink, blue, pink, blue, and it is increasing by one more diameter each time. Okay, and that type of reasoning, you guys, when you look at patterns like that, it's called inductive reasoning. Okay, a counterexample is a specific example that shows that a conjecture is false or incorrect. You can find a counterexample to show that each conjecture is false. So part A, the conjecture is that the product of two numbers is always greater than either number. All right, and here we have another conjecture that says all apples are red. Okay, so what we're being asked to do is find a counterexample that shows that this right here is false, okay? The product of two numbers is always greater than either number. Now, a lot of times when we're asked to find a counterexample, we try to go like in a general form, we try to explain it, but really it's just one concrete example that proves this false. So use actual numbers, don't use variables, just use constants and just show one example of why the product of two numbers is always greater than either number is false. Same thing here. We're then asked to provide a counterexample that all apples are red and show an example that that is false. Okay, so pause this video if you need to think about that for a moment. A good counterexample for part A would be -2 and +4. -2 times +4 is -8. And -8 is not greater than 4 or the -2. It's not greater than either of them. So this is a concrete example using constants, and it proves that conjecture false. Part B, one route would be showing a Granny Smith apple. That is a concrete example showing that the conjecture, all apples are red, is a false conjecture. All right, let's continue our discussion into section 2.3 on conditional statements. A conditional statement can be written in the if-then form. If something occurs, then something else will occur. If a figure is a pentagon, then it has 5 sides. A figure is a pentagon is the hypothesis, often denoted lowercase p, and it has 5 sides is the conclusion, often denoted lowercase q. Symbols for conditional statements. So we're going to use those lowercase p and those lowercase q's. Whenever you see a lowercase p, think, okay, that's the if statement, the hypothesis. Whenever you see the lowercase q, think that's the conclusion. Okay, if p, comma, then q. So this is a notation that you'll see sometimes for conditional statements. P implies q. And P with this arrow in between pointing towards Q. All three of these mean the same thing. They mean that if P occurs, then Q will occur. Symbols for what we call a negation. Negation is the negative of a statement. We use this symbol right here, the tilde. Okay, so if you see that symbol in front of the lowercase p, you would read that not P. Okay, let me show you an example of that. If our statement is the computer cover is red, the negation would be, let's get 2 of them up here. And we have a second example. The rarest blood group for humans is not group AB. All right, let's start with this one. The negation of this would be the negative. So we would say the computer cover is not red. You don't have to get fancy, just it is red, it is not red, negation. Let's try this one now. What would you write as the negation for that? If you said the rarest blood group for humans is group AB, you are correct. Okay? So each of these statements is the negation of the other. This did not start with the word not, and we added it. This started with the word not, and we deleted it. Okay? So either way, we've done the negation. A conditional statement can either be true or it can be false. A conditional statement is true if every time the hypothesis is true, then the conclusion is also true. So if you have lowercase p implies q like that, and if every time your hypothesis is true, so the truth value on lowercase p is true, then your conclusion is also truth value of true, then the overall conditional statement has a truth value of true overall. A conditional statement is false if there is a counterexample in which the hypothesis is true, but the conclusion is false. I'll write that in symbols. So if our hypothesis has a truth value true, but our conclusion has a truth value false, then this is not a false conditional statement. So overall, it would be considered false. Is the conditional statement true or false? All right, let's try some examples. If an angle measures 92 degrees, then it is an obtuse angle. All right, that is a conditional statement. Here we have our hypothesis. Here we have our conclusion. And let's see, there we have a 92-degree angle. It's obtuse. That one's twisted a little different, but it's still 92-degree angles, which is obtuse. This one's twisted a little different, but regardless of the orientation, it's still 92 degrees, which makes it obtuse, even if we go all the way in this direction here. So it's looking like, or it is, if an angle measures 92 degrees, if that is true, then your conclusion is always going to be true. It will be an obtuse angle. So this would make the overall statement have a true truth value. The conditional statement is true. Let's try another one. If a month begins with the letter J, then the month has 31 days. Okay, so this is our hypothesis. We're going to say that that's true, okay? So we're going to look at months that begin with the letter J, and we're going to check if, in that case, the month has 31 days. We're going to see if that's always true. If it is true, overall statement's true. If it's false, overall statement's false. Okay, January, June, and July, those are the 3 months that begin with the letter J. And if we count how many days are in each, turns out that that is false. The month June starts with J, but it only has 30 days in it. So if you have a true hypothesis with a false conclusion, then your conditional statement is false. Okay? You need it to be true, true to have a true result. All right, let's look at conditional statements, their converses, their inverses, and their contrapositives. I like to start with this symbol, this column right here to explain. Okay, so we already talked about conditional statements having this symbol. If P, then Q. Okay, so let's look at the converse. You take the P and the Q and you switch them. Okay? The if stays where it's at, the comma then stays where it's at. It's just you take the hypothesis and the conclusion and you switch them. That is called the converse. An inverse, I need to erase that circle, it's too big. Okay, the inverse of a conditional statement is if you take P and take Q, leave them where they're at, okay? Leave them where they're at, but negate each of them. You see that tilde symbol right there? So say, if not P, then not Q. Okay, P and Q stay where they are. You just negate them. And fourth option, the contrapositive of a conditional statement. That is when you're going to take P, you're going to take Q, you're going to switch them, switch places, and you're going to negate both of them. All right, so conditional, leave it how it is. Converse, switch P and Q. Inverse, negate P and Q. Contrapositive, switch and negate P and Q. All right, let's look at an example. If the measure of angle B is 160 degrees, then angle B is obtuse. Okay, this right here is P, and this right here is Q. So for the converse, we take Q and we take P. We say, if Q, then P. Check. For the inverse, we keep P where it's at, but we switch it to the negation of does not equal, and we leave Q where it's at, but we switch it to the negation of is not obtuse. Check. And last one, we take P and Q, we switch them and negate them. So angle B is not obtuse, then measure of angle B is not equal to 160 degrees. And each of these statements right here can have their own truth value. So overall, this one could be true or false, this one could be true or false, this one could be true or false, this one could be true or false. True or false for all of them. Okay. If two statements are both always true, or if they're both always false, then we call them equivalent statements. Now, it's an interesting word to use, equivalent. We're just saying that their truth values are equivalent. So if two statements are both always true, or if they're both always false, we call them equivalent statements. So if you're ever asked, okay, are these two statements equivalent? You want to check their truth values. And if they're both true all the time, or they're both false all the time, then they are equivalent statements. Okay, writing related conditional statements. Let's practice with what we just learned on the last slide. Write the converse, inverse, and contrapositive of the given conditional statement. Determine if each is true or false. All right, here's our conditional statement. If a figure is a square, then it is not a triangle. To do the converse, we're going to switch P and Q. So if a figure is not a triangle, then it is a square. That is a false statement. Figure cannot be a triangle, but it could be a circle. That'd be a counterexample, circle. The inverse would be if a figure is not a square, then it is not a triangle. This is a false statement also. Counterexample, a figure could not be a square, it could be a circle. So once again, circle would be a good counterexample. And contrapositive, if a figure is a triangle, then it is not a square. This is a true statement. Triangles are not squares. So you have a figure that's a triangle, it's not a square. That's true. And what about our first one there? If a figure is a square, then it is not a triangle. That one was also true. So the first one was true and the contrapositive was true. The converse and inverse were both false. Okay, that will conclude our discussion on sections 2.2 and 2.3. My name is Jami Emigh. Thank you for joining me, and I will see you next time for our discussion on section 2.4.